All right, so again, the height is just 1 over the length. And your problem, how long is that rectangle?
15.
15. It goes from 15 to 30, so it's only 15 long. It's not 30 long. So what's the height?
1 over 15.
1 over 15. So it's probably, they arrive between 20 and 25 minutes. So 20 and 25. How long, how wide is this?
5.
5. How tall is it? 1 over 15. So the area is going to be 5 times 1 over 15. 1/3. 5/15 or 1/3. Or 0.33, that's fine as well. Okay, good. So uniform distributions are going to be the easiest distribution we covered. We've covered binomial, normal, uniform. The only other one that you might get on the exam is going to be where I just give you, here's a frequency, a probability distribution, and here it is. I give you the x's and the probability of x's, and you just get it, right? So those are the 4 types you're going to get. All right, so now, this coming up, the next 5 minutes, we're going to talk about a really hard topic. I need you guys to focus really well for the next 5 minutes, because if you focus really hard and stay on top of it, it will make sense, mostly. If you don't, you're going to be completely lost. Does that make sense? I mean, it might totally make sense to you, or at least mostly. For all of you, at least should mostly make sense, right? Like, it's hard. It's a hard topic. All right. So here's the thing. My expected wait time is 10 minutes. Everybody follow that? If I sample 30 people, though, and find the average of those 30 people, so how long you've waited for the bus, how long you've waited for the bus, how long you've waited for the bus, 30 people and how long they waited for the bus, I take all those wait times, and I average them. I might not get exactly 10, right? I might get 11.24, or another sample might be 9.43. Everybody see what I'm saying? Good? Okay, so this is an average of 30 people, right? So let's say I take a whole bunch of samples and find the sample mean, the x-bar for each one of those. So each one of these represents a sample of 30. So there's a sample of the mean of a sample of 30. Here's another mean of another sample of 30. So each one of these numbers represents 30 people and their average. Good? This is cool. The central limit theorem says that these sample means will be normally distributed. In other words, they're going to be centered around the real mean. What's the real mean? What do we expect them to be? 10. They'll be centered around 10. And then, as they get further and further away, there'll be fewer and fewer of them, and they'll be less and less likely to their averages. So most of them are going to be right around 10, and then fewer will be further and further away. That's really cool, even though this came from a uniform distribution. If we take a sample of 30 or more, the sample means will be centered at the mean and then kind of make this nice normal distribution, which is really, really useful. We'll talk about why it's useful in a little bit, but let's talk about some of the details first. First of all, properties. Obviously, the average of those should be 10, right? What we expect to get. We're all on board with that, right? So the mean of the means, so it's kind of hard to wrap your head around these because they're means. So my friends and I in grad school would kind of say, oh yeah, the mean of the means, because that kind of helped us kind of realize we're talking about a mean of means, so we kind of realized there's another layer in there. The mean of the means is just give me the regular mean. So in our last case, it'd just be 10 minutes. That doesn't change. However, the standard deviation of the sample mean, so in other words, sigma x bar, the standard deviation of the means, sample means, is going to be your regular standard deviation divided by the square root of n. It's going to be smaller. It's super cool. It has this relationship. So those two things you should be writing down on your notes. They're on the back page, I think. Right? You need to have those two things. You need to have the mean of the sample means, mu x bar, is equal to the regular mean. And sigma x bar is equal to sigma over square root of n. Why is that? The mean is obvious. I think you guys all kind of followed that. Yes, those means should all be about 10 minutes, and they should be, on average, those should be 10 minutes. But let's look at sigma x bar. So I remember Steph Curry in 2016. That was a year like that he was doing three-pointers all over the place. He had like 2 or 3 50-point games. This is the one where like he took the ball in from like halfway, let like 3 seconds to go, and like almost from halfway shot that three-pointer. So, so a 50-point game for him will be right around the borderline of unusual. Do you guys see what I'm saying? It could happen. We wouldn't say it's crazy. We would say, oh, yeah, that might be kind of right around the edge of unusual. But if I randomly sampled 25 of his games and found the average of 25 of his games, there is no way that I'm going to get an average of 50. Right? It's not going to happen. It's because they'll be, for every time I pick a really big game, a 50-point game, I'm probably going to grab a 10-point game, and they're going to kind of balance each other out a little bit. So the mean of 25 games is going to be really close to his regular mean of 30 points. It's going to be because of that balancing out, right? Every time I grab one of these, I'm going to grab one of those. Typically, right? Maybe not, maybe, but it's going to tend to be kind of right around here. After you take 25 of them, you're going to get a chunk of low ones along with a chunk of big ones. So let's take at the standard deviation, and you guys can see what I'm talking about. So this red one is just for one game, right? On average, he scores 30 points. He might have some games that are 10 points, very few. He might have some games that are 50 points, very few, but it kind of goes like this. But once I take, so let's take a look at his standard deviation. We know that typically about 2 standard deviations for the mean is going to be that kind of unusual levelness, right? So I might say that standard deviation is about 10 points. Reasonable? I think it's reasonable. That's reasonable. Just go with me. Okay, I'm getting no feedback. It's reasonable. Trust me. Okay, so let's find an average of 25 games, what his standard deviation might be. So by sigma x bar, the standard deviation for an average of 25 would be the regular standard deviation divided by the square root of n. My regular standard deviation is 10. My n is what? How many games?
25.
25. What's the square root of 25? 5. So 10 over 5. So we figure about 2. Which means that, in general, unusual would be about, just 2 points. His standard deviation is going to be a lot smaller. Like if I took an average of 25 games, I might get something more like 26 to 34 in general, usually. Why? Because again, you have this canceling out. I'm never gonna get 25 games averaging to 50 points. Right? Because I might grab a couple of high ones, but I'm probably gonna grab some of the low ones to go with it, and they're gonna balance out, so they kind of come right around in here. So that's the neat thing, is when you take a sample, a large sample, then you have this kind of balancing out where the high ones get balanced out by low ones, so that you don't have crazy high stuff out here, and your standard deviation is going to be a lot smaller. How much smaller? Divide by square root of n smaller. That's how much smaller.
So this only works when you get so you started with 50 games or 30 games?
No, it only works when you have a sample size of 30 or more.
Okay.
So let's talk about that. There are conditions. If your original variable is not normal, like that buses, we talked about those buses a second ago with the uniform distribution. That's uniform is not normally distributed, right? That's definitely not normally distributed. But if I take a sample size of 30 or more, then the average of those, the mean of the means, will make a normal distribution. The sample means will form a normal distribution. However, if the data is already normally distributed, then it doesn't really matter. I could have an n of 1, and it's already normally distributed, so it's fine. Incidentally, if my n was 1, what sigma over square root of 1 is just what? Sigma. What's the square root of 1? 1. So sigma over 1 is just sigma. So if my n was 1, it would just be the ordinary standard deviation. Nothing would change. Okay. So you guys have these down in your notes already? Yes? Everybody's written them? All right. So do problem 7 on your lab. In other words, find mu x bar and sigma x bar.
Can you go back to it?
Which slide?
Just the one, yes.
That one?
Yeah.
Okay, so mu x bar. Mu x bar is the same as what? Mu. So it's just 86. Right? And then how about sigma x bar? It's the same as sigma over square root of n. So again, remember, these are just labels. Anytime you have this lowercase, this little subscript, these are just labels. And it could be the sigma of the mean. So what's my sigma? 8 over square root of n. N is 24. What did you guys get?
1.63.
1.63, 1.6. Good? 1.63. We'll put 1. Sure, 1.63. Sure. Okay. Good. Why is this useful? Megan, go ahead and read.
One way that it is useful, there are many, is that if you take a sample and find a probability that the mean of that sample will fall in a certain range regardless of the frequency that's heavily distributed.
Right? So for example, so the thing is that the reason why this is useful is I want to do, normal distributions are beautiful. They're symmetric. I know the probabilities of being between any 2 points, right? I can find, if you give me 2 numbers, then I can find the z-scores and I can find the area between them, the probability between them. If I do an experiment, as long as I take a sample of 30 and take their average, then it falls into a normal distribution and I can use those great properties. So that's why it's really important and useful to have this idea, because normal distributions, super easy, they're reliable, we can kind of predict off of them. Okay, so here, Jay, go ahead and read.
Example, hours of television. A.C. Nielsen reported that children between the ages of 2 and 5 watch an average of 25 hours of television per week. Assume the variable is normally distributed and the standard deviation is 3 hours. If 20 children between the ages of 2 and 5 are randomly selected, find the probability that the mean of the number of hours they watch television will be greater than 26.3 hours.
Great. There are a lot of numbers in there. So let's kind of go through this. Children between the ages of 2 and 5. Okay. Well, I don't know. Maybe I'll kind of move on from there. Watch an average of 25 hours of television. Average of 25. What's that?
The mean.
That's my mean. Okay. Assume the variable is normally distributed. I need that. That helps me because then it doesn't have to be 30 or more. Right? Because remember, if it's not normally distributed, I need a sample size of 30 at least. Okay. And the standard deviation is 3. Ooh, that's easy. So that's my, 3 is my what? Standard deviation, so that's my sigma. Good. Okay. If 20 children between the ages of 2 and 5 are randomly selected, 20 children are selected. That's my n. So find that randomly, right? Find that selected or chosen or surveyed. That's your n. Find the probability. Okay, so this is my one clue. That this is my, well, this is one of my clues. That it is an x bar and not a regular x. So the stuff we've been doing so far today has been regular x values. Find the value of one candy bar being between 200 and 220 calories. Just one. Now we're talking about the probability that the mean of a bunch of them, an x bar. So the difference between x and x bar is important. X is just one. X bar means the average of a bunch of them. So here we're talking about the mean. Whoops, draw it better. The mean will be greater than 26.3. That's my x bar. So I don't have an x, I have an x bar. So those are the two clues that this is a mean of means type problem. We have this mean thing here, and we have this n over here, because remember the candy bars? The probability that a chocolate bar will have a calories between 200 and 220 calories? I didn't have n. I only had one candy bar. There was no n. So when you have an n, that's your first hint that maybe this is one of those central limit theorems, one of those x bar things. And then look for the probability of a mean, not probability. Okay, so you're always going to have a mean. Let me rephrase that. So we have a mean. We have a mean here as well. But this is the probability of a mean. Do you guys understand the difference?
Yeah.
So my mean is greater than this. So we're talking about the probability of a mean. So then I know that this needs to be, I'm going to have a sigma x bar, and not just a regular sigma. So I need to find sigma x bar. Sigma x bar, sigma over square root of n, 3 over square root of 20, and then we'll use that. I do not like it when they do this thing here, because I think we should not have those. So then we're going to do a nice little, oops. Our next step is going to be finding our z-score. So we'll find our z-score. How do I find my z-score? I take my value. What's my value? It's my x bar minus my mean over my standard deviation. So that's going to be my mean. My x bar is, my value I care about is 26.3. Right? This is the one I'm checking out. The probability of that 26.3 is something. Minus my mean, 25, divided by my standard deviation. But it's not my regular standard deviation, it's my sigma x bar. I use this one instead. That's the twist. I don't use regular sigma, I use sigma x bar. So I use 3 over square root of 20. And you have to find this first, find this separately from this, and then divide them. That's the easiest way of doing it. Because otherwise you'll get some crazy, insane answer. If you do this, you should get, I know, we'll do this. 1.94. And if you don't do that, you're going to get something insane like, I don't know, like 14 or 12 or something totally off. So now I have my z-score. I can draw my picture. There's my picture. Notch in the middle. Where's my z-score? 1.94. It goes over here somewhere. Draw a line straight up. Do I want more than this or less than this?
More.
Greater than. Yeah. More than. So it's on the right side. Which means my other one out here would be positive infinity. So then I'm going to do normal CDF. No, wait. Is that right? Yes. Yep. Normal CDF of 1.94, comma, some large number. I don't know. 81? What do you guys get? 02619. 262. You guys feeling all right with that? Okay, I think you have your lab problem to do. So you guys do lab problem 8. Okay, so now Ian's gonna explain it. Ian, go ahead.
In order to find the z-score, you take the difference between the average, the mean, and x bar.
Right, so maybe you want to go ahead and find what some of these things are. So what's this guy here?
No,
24.3.
look. It is not doing
What's 24.3?
Or mean.
That's mean.
Yep, that's the mean.
I see the
What's 2.6?
Standard deviation.
Standard deviation, good. What's 33?
And
N. Everybody good with that being N? And then we have this guy here, 23.6. That is our, anyone? X bar. Okay, great. Go ahead. All right, so go ahead, so proceed.
so once you take the difference between x bar and the mean, then you divide that by the standard deviation divided by the square root of n. And you get a -1.11, which is the z-score that you're going up until. It's less than -1.11. And then you almost see the -99 or somewhere. Negative value.
Great. And then you do a picture. So you gotta make sure you have your picture. You have your, put your z-score and you want less than. So you're gonna do this part out here so that you know it goes out to -999. And you probably also have like a little spot out here maybe that says, oh yeah, this is negative infinity. Good? Okay. You might have used -1.10 depending upon how you rounded off this stuff in here. And then you'd have something a little bit larger here. You might have 0.1348. That's fine too, as long as you're consistent with that. It doesn't matter. Okay. Yeah. I don't care. As long as you have one of those two, you're good. As long as you show your work and it's consistent, then you're fine. Okay. So I think I just want to take
Yeah, no.
a few minutes and go over the project.